Good evening, everyone. My name is Austin Bonander, and I maintain a little crate called SQLx. We'll get into that in a minute. I want to thank Svix for inviting me out here. I've had the pleasure of working with both Jonas Platt and James Brown on various open source projects, and I've always been impressed by your professionalism. So I'm going to go ahead and start. About me. I've been a software engineer for 14 to 15 years, depending on when you start counting. I'm entirely self-taught, which is, I feel, relatively unique in this era. And I started freelancing right out of high school, doing Android apps for literally a couple $100 a pop. And so I've actually been a participant in the Rust community since before 1.0, which is, May 2015, if I remember correctly. My first post on the Rust subreddit, July 2014, and my first pull request to Rustlang was in August. So I'm part of the old guard here. I submitted PRs to enable procedural macros, the function-like procedural macros, and proc macro attributes in 2017. Although in reality, that only consisted of about the last 20% of the work. It was the last mile. Most of the work had already been done by core team members at the time, Jeffrey Seyfried, Nico Matsakis, and Nick Cameron, whose mentorship was invaluable. And so in total, I've submitted 33 PRs to various Rustlang repos. Not all of them merged, but it has dropped off since I've actually started using Rust professionally. Which started circa 2017. And since September 2020, I've been a member of the Rust subreddit moderator team. So I maintain a little crate called SQLx. Has anyone heard of it? All right, about half the room. Anyone use it professionally? Okay, less than half the room, but that's normal, it seems. So SQLx is an async SQL client for Rust, and our gimmick is that we have type-safe queries verified at compile time without anything like domain-specific language, like something like Diesel. So some quick facts about SQLx. We started work on it in June 2019. The principal authors were Launchbadge CTO Ryan Leckie and software engineer Jana Akhtarov. I didn't get started on it until sometime later. Our original work in progress name was DBX, and then Mason for some reason. Your guess is as good as mine. I don't even remember those discussions. So I conceived of and began prototyping the query macro infrastructure in November 2019, and that's what gives you the compile-timed check queries. Building on my previous experience working on the proc macro system in the Rust compiler. So our first public release, which was actually 0.1.1, because 0.1.0 was name squatting, was December 2019. We initially only targeted async standard, which if you're familiar with it at all, is probably most recently hearing that it's been obsoleted. And there's reasons for that. And then in zero, pretty quickly, almost immediately, people asked for Tokyo support. So we added that in 0.2, and we've been using it in our own usage ever since. So we initially only supported MySQL and MariaDB and Postgres. I will use MySQL and MariaDB interchangeably here. They're close enough. They've started to diverge, but we actually used the MariaDB reference documentation when we were building it because it's better than MySQL's. And then we added SQLite in 0.3. We spent a lot of time trying to figure out how to make SQLite work in an async environment, and we had just ended up using threads. And we also had added support for Microsoft SQL Server in 0.4, but we later ended up removing it. We never really finished it. And it didn't support TLS, and it didn't integrate with the macros, and it was getting tons of bug reports, so it just kind of made more sense to get rid of it. So the reasons we created SQLx, to begin with, there was no async SQL client for async standard in 2019. Excuse me. So we were initially heavily invested in the Tide web framework, which has not been maintained in about 4 or 5 years, but that was what Ryan was actually most excited about. So we initially invested in the async standard ecosystem, but as you know, as history shows, the direction ended up swinging towards Tokyo. We had previously been using Diesel a lot in our initial forays into building Rust backends, and we had also used Juke in Java, which is almost the exact same thing. It's the same idea where it's a typed query builder. And so, you know, we had a lot of problems with that kind of library. Like, for example, with Postgres, we love Postgres, but it was kind of hard to use to its fullest extent because of the massive catalog of functions that Postgres has. If they're not modeled in the DSL, like, you got to do that yourself, and that can get really annoying. Diesel also used to generate very obtuse compiler errors. You know, you're talking, you know, X is not implemented by Y, you know, and so on and so on and so on. And to be fair, to be very fair to the Diesel team, especially Weisnick, Georg, similar, he has actually submitted a ton of pull requests to the Rust compiler to get those improved, and he was the one that championed the diagnostic attributes to specifically make those a lot better. So I have to give them credit for that. But there's also just a lot of little annoyances, like if you wanted to add a where clause, which is pretty common for a SQL query, you'd have to remember that it's actually .filter in Diesel, because where is unfortunately a language keyword. And like, that sucks. It's not Diesel's fault, but it was just annoying. For really complex queries, especially if you're trying to use you know, Postgres specific stuff, you end up having to write SQL anyway. And then you lose all of the benefits of the type checking, because, well, you have to model all of it yourself, and at that point it's just getting in the way. And also, Diesel did not support async till 2022, and that was just a bandwidth issue on their part. It's not really their fault, but it was an issue. And actually, my former boss, Ryan, was the first to create a async wrapper for Diesel. And that was actually Tokyo Diesel and then async Diesel. But now the supported one is Diesel async. And also because we wanted to. We just wanted to see if we could do it. You know, we were that was just kind of our attitude. It's like, screw it, let's see if we can. So SQLx has gone through a number of revisions, and there's a number of challenges. This list is not exhaustive by any means, but there's 4 I want to go through quickly here today. Cancellation bugs, type checking in the query macros, always been an issue. Supporting third-party drivers, and I'll explain what that means in a minute, and performance. So, cancellation. Does anyone know what that's referencing? The $1 million mistake. Oh, so that Tony Hoare coined the term billion-dollar mistake, referring to null pointers. And you could argue that cancellation is at least a sync Rust's $1 million mistake. You could argue that. Because the core fact is that callers are allowed to not pull futures to completion. And I didn't go into explaining how async and futures are desugared and how they all work. There's resources online, like on Tokyo's website, that explains how this works. But you're allowed to not pull a future to completion. The only requirement is once a future is pulled, its location in memory has to be stable, or its drop handler must be called so it can be cleaned up. And this is the core guarantee enforced by PIN, which is kind of, a lot of people don't really understand what PIN is for, and it's specifically to enforce this. And so it's required because when you desugar async code, it ends up generating structures that point back into themselves. And so without having extra code to fix up those pointers or encoding them as offsets, you need a stable address in memory. And there's also, you can also have intrusive wait lists where the future struct itself can be a node in a linked list of waiting tasks. So you don't have any extra dynamic allocation on that, which is very powerful. So when you drop a feature before it completes, it's called cancellation. So this is something that was not really explained very well in all of the educational material when async await was first introduced in Rust. Any dot await is a point where execution can diverge and never return. So think about that. Any dot await, your code can just stop. And that can be an issue because if you mutate any kind of shared structure where that mutation can be observed afterwards, you have to leave it in a consistent state between await points or else you're going to have bugs. And as you can guess, we ran into some bugs. Something similar came up in the past. I didn't add a bullet point for it, but panic safety. When panic catch unwind was made safe, there was a lot of discussion about this exact problem in the regards of panicking, but they just kind of let this slip by. But it is actually a feature, and we'll see why. So async in lots of other languages, and to be fair, I don't have a ton of experience with this because I've been working primarily in Rust for the last 8 years. But you have to wire in cancellation. If you want an async task to be able to stop, it has to be aware of that. So like JavaScript, you have a abort controller, and your task has to check if it's been aborted. C# has the cancellation token that you've got to thread through, and Go has context.withCancel. I don't know Go, and I don't want to learn. So think about in the context of web servers, this is a possible denial of service vulnerability because you can have really expensive operations. You make a call out to a database, that's going to tie up probably a thread, probably a decent amount of memory, and a very limited set of database connections. So all an attacker has to do is identify the most expensive route in your application, call it in a loop, and watch it crash. So that's something to kind of be concerned about. So in Rust, Hyper, ActiveWeb, Axum, basically all the web frameworks, they use cancellation. When a client drops the connection or stops responding, they just abort the task and drop all the futures. So you don't really have this tie-up of resources. So this is actually the most recent cancellation bug we fixed in SQLx. So this is our transaction type, which is our RAII wrapper for transactions. So you begin a transaction to create it, and on drop it rolls it back, or you can commit it. So this is the code that actually constructs that. And this method here is what actually calls into the driver-specific code to issue that begin statement. So does anyone have an idea of the bug here? No? Okay, the problem is that, especially if you have pooled connections that are being shared by multiple tasks, this begin command can be in flight when this future is dropped, meaning you have a connection that's returning to the pool that's stuck in a transaction, and that obviously can cause a lot of bugs. It can cause, well, you'll get an error if you try to begin another transaction, or you just have data that won't commit. So what we actually need to do here is create our RAII wrapper here, which will run a rollback command on drop, and it just queues it. It doesn't wait for it to finish, but it just queues it. So that way the next task that uses the connection doesn't have to deal with that. And that was a very simple change. If you find this code on main, I've editorialized the comments a little bit just for clarity, but that's the subtle kind of things you have to pay attention to when you're writing async code, especially with shared state. So the solution is to just spawn more tasks. In general, spawn tasks, so if you call Tokyo spawn, which is the most common entry point, those can only be canceled pretty much explicitly. You either have explicit methods on the join handle in async standard small Tokyo to explicitly abort the task, or the runtime's shutting down and it doesn't matter, we're dying, it doesn't matter. So the plan is to spawn the connection state machine, because right now, any call into SQLx directly goes into the connection state and starts making IO calls and all that stuff. But what we actually need to do is move that to a background task so we have control over when it quits, and we'll just talk to it over channels. We didn't do this initially because we were really worried about performance. We think, well, it's got to be slower talking to a background task than just directly interacting with the socket and all that stuff, right? Like, it doesn't make any sense to spawn it on a background task. But Tokyo Postgres, using this exact execution model, has been beating us on benchmarks for years, and I'll give them credit for that. So the benefits of that is you can do better parallelism, because the connection can be decoding rows from the socket while your application is running business logic on what's coming in. You can also have pipelining, which means you can have multiple queries in flight, and you should look that up if you're interested, but that's mainly about not paying the round trip time to the server as much. I think it also results in better code locality, because once it's in the connection state, it stays there. So all those data structures remain in the CPU cache and don't get invalidated. And it results in smaller futures, because the deeper your async call tree is, the bigger the future is, because it's got to contain the state for all those internal ones. So there's actually an open PR by a contributor, Joey DeWall, who I should call out because they've made a number of high quality contributions. So that's open specifically for the Postgres driver. That's the pull request number there if you'd like to look at it. Ideally landing in a backwards compatible release, because it's purely internal. Next issue is type checking in the macros. Always been a big problem. So the biggest issue is null safety. So our code generation in the macros is actually driven by prepared statements. So we send a query to the database and ask it to prepare a statement, and it spits back some metadata, including types. And in some cases, specifically MySQL, it will tell us whether a column is null or not, which is actually very cool. You'd think that would mean MySQL is my favorite database, but it is not. So if you have a table like this, and this is literally copied from one of our tests. If you prepare this statement, this is just the table for an idea. This is a screenshot from Wireshark, because this is the easiest way to visualize this structure, but you can see we get a flags field here, and one of the bit flags is not null. And that's generally pretty correct in my experience. We've only run into it a couple times, I think specifically with MariaDB, where that's not been correct. So that tells us whether the field needs to be wrapped in option or not. Historically, we have not avoided parsing the SQL out of queries to understand the structure of them. So for Postgres, it gives us types, but it doesn't tell us nullability. And that's a big issue, because you don't want to deal with all your types being wrapped in option. That's annoying. So if we have a table like this, and this again is just copied from one of our tests, so excuse the complexity. But what we do with Postgres is we actually, if this is the query down here, this explain verbose is what we actually send to Postgres, and it spits back this JSON structure. And, sorry, I hit the mic there. And what this tells us, mainly what we're looking for is what tables a column comes from, because Postgres doesn't tell us that inherently. So we use that to seed our null checking data. So we actually go look up those columns and see if they have a not null constraint. And then we're also looking at the join types, seeing if it's an inner join or a left join, any kind of outer join where half the result can be null. and then we update with that. SQLite gets a little more complicated because SQLite, when you prepare a statement, it'll only tell you the declared types of columns. So any expressions, you're SOL. You're only going to find those out once you've started executing the query, which for our purposes is too late. So this means we have to type and null checks SQLite queries, which gets pretty involved. And what we do with that is, sweet SQLite, when you prepare a query, it generates bytecode to execute that query. And we actually step through that bytecode to see where columns come from. So again, with a table like this and an explain query, we get back a list of instructions like this, and we decode these instructions to see what happens. And mainly what we're looking for is these column opcodes. These column opcodes. I thought I was going to select it, but it's a freaking screenshot. So we're looking for these column opcodes, this result opcode, result row opcode, and then either a null expression or a null row opcode, which causes all of these column opcodes to decode nulls. So that then seeds our null checking. And we also look for the types of expressions, or if it's coming from a column, then we just look at the declared type on the table. So that's pretty complicated. That's about 1,500 lines of code that we shouldn't really need. And obviously, it's far from perfect. So we err on the side of false positives, so wrapping types an option when we don't necessarily need to, and that's to avoid errors at runtime, because if we get a null but we're not expecting a null, well, we can either error or panic, and that's not great. So yeah. As you could probably tell, both the Postgres and SQLite implementations are pretty dang fragile. Any changes to the query will result in significant changes to the query plan because it's not supposed to be stable. Those outputs aren't meant to be stable. They just are de facto stable. But they will change if you make small changes to the query, and that can lead us to infer the wrong things. One thing a lot of people complain about is functions like count. Type check is nullable when obviously it shouldn't. And that's just because we don't introspect function calls, which is a problem. And so compiler errors, I know, I harped on Diesel for compiler errors. Our compiler errors are not great. I hope to work on them, but you get a lot of just expected type, one type got another. But at least you can expand the macro and kind of try to see where that's coming from. So maybe we should just parse the SQL. Back when we started, there wasn't any crate that could parse SQL for us. The SQL parser crate existed, but it only covered the ANSI standard SQL, which, if you're familiar with it, is useless because every database out there does their own dialect. And writing our own parsers was basically a non-starter. That's also another few thousand lines of code we didn't need to write. So now the SQL parser crate actually covers a ton of dialects, including Postgres, MySQL, and SQLite, even ClickHouse. So it basically has everything we need. So we can just look at the structure of the query itself and be able to tell with some seed data what columns are null or not. We'll probably still need to connect to the database at compile time. MySQL, we won't need to parse the query because it already tells us everything we need. Postgres, we'll do it for type checking, so we don't have to implement that part. We also will need to be able to look up table schema to know kind of what's going on, maybe, I'm not sure. But also to resolve custom types. So if you have a custom name type in Postgres, Postgres does not send that name over the wire. Instead, it sends an OID, which is just an integer. So we need to be able to resolve that name to that integer to be able to send and receive those types. And then SQLite, obviously, for column declared types, and that's going to seed our null and type checking there. What's cool is that because we are async, these analysis passes could run while the prepared statement request is in flight. So we won't necessarily need to pay for that as much. because the network call is probably going to be slower anyway. What's not planned, what's often requested is like why I can't, you could just look at my migrations where my scheme is defined and just figure it out from there. And it's, people that ask that I don't think quite understand how complex an ask that is. We'd have to handle create table, alter column, create function. It would get very complex very quickly. So we'll probably always rely on a connection to the database. There's also a lack of interaction with the from row derive. So users often expect something like this to work, which is very sensible. So this is query as, so you're specifically requesting a named type, a named structure here. And people expect to be able to, like say, use these kind of rename all attributes, which if you've used Zerde before, you've probably seen something like that before. We support that, but the problem is this derive only works with the non-macro versions.
Do you want to, I don't know how much more you have, just so we can also save time for questions and other speakers.
Oh crap. I can skip through this. So that's a significant refactor. Third-party drivers. So we want to support third-party databases. The problem is we don't have the bandwidth for that. So we do support out-of-tree drivers, and there is one that is trying to do that. But the problem is right now it supports building new facades. So ideally we'd like to be able to just cargo install, but we'll probably need a new IPC protocol for that. Performance, people complain SQLx is slow. They always look at these benchmarks. This is the bane of my existence because they look at this, they see Axum should theoretically handle millions of requests a second, and then they look at the SQLx benchmark and it handles a fraction of that. But one thing no one ever complains about is that Deadpool, which is another pooled connection implementation, using Tokyo Postgres, the same database client as number 7 here, is also down there with us. But we're faster than Django. That benchmark actually cheats. It's been micro-optimized. So each CPU gets its own current thread runtime, so there's no contention. Each thread gets its own listen socket and accept loop, dedicated DB connection. There's no contention, but there's also no support for transactions because that needs immutable access to the Tokyo Postgres client, and that code doesn't support it. So SQLx and the Deadpool benchmarks use the standard Tokyo multi-threaded runtime with a single connection pool. So there's a lot of contention with that. That benchmark also only tests one route at a time, which means uniform relatively CPU load, so there's no benefit from work stealing, which is what the multi-threaded runtime is designed for. So it's kind of unrealistic. So SQLx is actually not that bad. As you can see, there's Tokyo Postgres. The text is really small. I apologize. But there's SQLx, there's Diesel async. For MySQL, it's even closer. Everyone's bad at MySQL for some reason. But we're within an order of magnitude. And this is Diesel's own metrics. They run these periodically. They compare a bunch of different clients. This is taken straight from this page over here. So yeah, and it's gotten way better. So the top lines are SQLx. This has come way down. And MySQL, the way these lines all stick together makes me think there's something screwy going on here. And this is since they started running the benchmarks. So these graphs are really busy, and I think they could do better, but I'm not complaining. I didn't do it. So we also want to rebuild SQLx pool from the ground up. I want to get rid of that contention, ideally by having threads select and lock their own connections. I'm also replacing some callbacks with a pool connector, so you have full control over the establishment of a connection. You can do dynamic credentials retrieval, your own load balancing, your own back-off loops. And we also want to give better feedback on connection errors. I didn't realize that any errors that we don't consider retriable, we propagate out immediately. But any that we consider retriable, which includes connection not reset or not reachable, we just eat without logging. I didn't realize that. And part of the problem is, you work on a code base like this for so long, you forget how parts of it work. So need to make that better. and better observability overall, better integration with tracing. Ideally, it'd be cool to integrate with Tokyo Console, and then you could actually see your connections being established, checked out, and returned in real time. I think that'd be really cool. So conclusion, going into 2026, 0.9.0 release is currently in alpha. If you're interested, please go try it. There's a new config format that lets you set a lot of global overrides, so you should have to do type overrides in the queries a lot less, and you can configure migrations. There's better support for multi-database workspaces. We also added support for the small runtime, which is the official successor to async standard. Wasn't as hard as you'd think, because it turns out async standard is just about 6 different crates in a trench coat, and small uses most of them. So though the constituent crates are still maintained. Lots of other changes. See our change log on our GitHub for details. Just go to github.com/launchbadge/SQLx and find the change log there. Next alpha release, I'm aiming hopefully around Christmas. With that, pool changes. There's a number of other breaking changes in the wings, and with a full release sometime next quarter. And we're also moving to a new GitHub organization. And this is because I haven't actually been a Launchbadge employee for the last couple of years. So we're moving it to a neutral organization, so we don't have to pay for seats. Rest assured that Ryan Lucky and I, my co-authors, we're still good friends. We actually have a private channel on the SQLx Discord where we mostly BS and share memes, but there's a few times we talk about SQLx. If Ryan ever finishes it, there's going to be another crate that's going to be hosted there. So yeah, don't I work for a database company now? Yeah, I joined ClickHouse this past September. I'm now the...
One more minute, just so we can keep things on time. I'm so sorry.
My last slide.
Okay.
Sorry. So I'm the official ClickHouse REST client maintainer. I know someone, I'm told someone gave a talk last month about some issues with the ClickHouse client. Was that you? Yeah, so we're working on that. That's my next big project. We're still discussing how ClickHouse wants to support SQLx, but we have this comment on our tracking issue for ClickHouse support from 3 years ago. That's actually Alexei, CTO and co-founder of ClickHouse, saying they want to see SQLx support. So one of my goals this next year is going to be building a ClickHouse driver for SQLx. So yeah, Q&A, contacts. If you're interested in ClickHouse, join our Slack, clickhouse.com/Slack. There's a Rust channel. There's a SQLx Discord. That's what the QR code is for. And my boss did want to mention that ClickHouse is hiring. We don't have any Rust-specific positions right now, but if you have experience in C++, Golang, cloud infrastructure, full stack, there's a ton of openings there. Go check it out. Yeah, join us. Questions? Cool. Thank you.
Yeah, well, I'm definitely not from Antithesis, but I did take a really disgusting slide deck and slam it into Gemini 3 Image Pro. So I definitely have to make this a tool to convert lame slide decks, and you'll watch the design of this slide deck completely nosedive when I got bored of sitting there babysitting image generation. But yeah, I'm going to talk about adventures in deterministic simulation testing. For those of you who don't know, we call it DST a lot. It's basically taking your code and putting it in a box so that you limit its interactivity with the outside world, such that you can recreate the same environment for it every time. You can also think of it as like pure functions, but for actors, where you're basically building something that you give it the same sequence of events, it's going to give you the exact same output every time. And the key here is that you want it to behave the same across both real time as well as interacting with external systems. And the reward from this is replayability, the fact that you can just replay events and you're going to get the exact same thing over and over again. I know, as I've built code that's scaled to like tens of millions of monthly active users, you'll always get someone who hits this crazy edge case. And it's like, just like the, planets were one way, the, Comcast was down like it is every 5 minutes, and then AWS was complaining that Google Cloud was giving bad DNS queries, and whatever happened, you get this one error and like a transaction gets thrown out in a way that like you were like, this is impossible in the code, and then it was apparently possible. So the whole point of this replayability is that we can take some set of events that always recreates that error, and we can just replay it over and over and over again while we're developing against that to make sure that we can actually get rid of those issues. Now, the main sources of non-determinism, which like you totally have to separate from your code that you care about, is time. So think anytime you go to check a clock, you go to get a timestamp from the system, async runtimes, and network and disk. Any sort of thing that's not basically a memory access is non-deterministic. The first one is time. Basically, you have to reduce it to a single source of time, which is pulsing. You can't check the clock because any time you check the clock, you are assuming that the clock moved at a constant rate, which it just never does. Even atomic clocks, they move at a much higher accuracy, or much higher precision, I should say, but clocks don't actually move at a constant time. So if in real time you checked between two periods of time, the amount of time that could have passed could differ if you do that same interval check. So your code cannot directly access the clock. It has to receive pulses from the external system that says it is now this time, and you have to respond to the passing of time. Hey, did it pass some threshold I was waiting for? Async runtimes, a lot of them introduce randomness into how they schedule tasks, a lot of them using the clocks to do so. The main technique here is just to keep things single-threaded. That keeps it pretty deterministic. If you do need to move things into the background, you can have per actor async runtimes. That way you don't get them conflicting with each other and fighting against each other. You can use background threads, and then you can even look at I/O queues. This is how I/O U-ring works. If anyone's ever played with that, it's you submit to a queue and you wait for a response, and you can kind of see that I/O U-ring is an actor that kicks off background threads effectively. And external devices. Anytime you access something that's basically not the memory bus, and in reality, even the memory bus and your cache lines, they're going to have some level of variability, but it's a lot more, it behaves a lot better than external devices. But if you're going over the network, you can lose packets, networks can fail, you're talking to other physical devices across physical wires that can be bitten by sharks or unplugged by dogs. And even disks. Disks can have latent sector errors. You can burn out traces on a motherboard. There's all kinds of reasons why you can get varying time between responses, varying success of data, returns. There's just lots of non-determinism when you go outside of your main memory space. So it looks a little intimidating, so I'll talk about some common patterns that would be translated. So instead of sleeping, what you would do is you would store some future time, and then you would wait until a time pulse progresses past that. Instead of making an HTTP request from your logic, because now you're talking to the network, you instead send a message out to an HTTP actor, which will eventually return the response as a message back to you. Instead of a file read, you would pass requests off to a disk actor saying, hey, can someone please read this file and give me the response? Instead of directly handling WebSockets, you would have a dedicated WebSocket handler that would then pass messages back through your system. If you're doing any heavy I/O, you want to just take the request for that, run some stuff in the background, and then when you're ready to provide that answer back to the system, you can return it on the next tick or receive. We'll talk about the interface in a second. That's basically how I/O U-ring works. And sort of through this exploration, I made a minimal Rust crate. Definitely don't use it. It's like super hacked together. I mean, I think it's pretty good, but I'm not going to support it if you use it in production. So, probably it's a reference implementation. We'll call it that. But it's really simple. It only has a few concepts. It has a message bus, a simulator, and an envelope. Nosedive time. Just screenshots of the package. Basically, the way it works is the system is built on a message bus. This message bus is single-threaded. It takes a concept of subscribers, which I'll show you in the next slide, and it just has an internal queue, which it handles messages. I actually made mine so you could do a number of queues, so you can have priority messaging if you have very low latency services that need to get messages across faster. Like, I want to get this file read from my database or this byte range read across much faster than I care about serving some statistics up to a web server. You want to be able to prioritize that, make sure you're not clogging it. And it's really simple. You just start it. It runs in its own dedicated thread. You add these subscribers, which have a destination name. You can publish envelopes from the outside system into the system, and then you can choose to stop it. A subscriber, this is that receive tick interface I was talking about. This is your actor interface right now. These are the only two functions you can expose to the outside world. Receive is used when you have a message in the message bus that wants to be delivered to that describer. So the system is saying, hey, here's a message for you, do something about it. And you are allowed to return a vector of envelopes saying, oh, something happened in the system, I was woken up, I did something, here's what I did as a result. Or you can just return nothing in the case of like, I have to do nothing, or I've gone ahead and launched this in a background task. And includes the system time. That's important because the more we can get updates about how much time has passed, the faster we can react to it. And then there's tick, which is basically you haven't gotten a message, but I'm going to notify you about the progression of time on some interval, just so if you were sleeping and I'm not going to send you a message for 10 minutes, you're not going to have a 10-minute drift on when you can respond to alarms or whatever internal timers that you want to send. So no internal sleeping, you wait for tick. No async run times. Random number generation must be seeded at launch. You can't just take one internally. And you should never care about the tick interval. You shouldn't expect it to happen at some rate. You should only know that at some point, receive or tick is going to be called with a timestamp, and that's when I can react to the passing of time. Envelopes are super easy. It's just a box around a message. Message is just like some send plus thing that says I can pass it over channels. Priority is that functionality I mentioned where you can just change priority messages. And then destination is that named subscriber that you actually want to pass a message directly to. And then the sort of the S part of DST, the simulator. The simulator is effectively the message bus, but it allows you to control the passing of time. So the message bus effectively will tick for you, so you can kind of just say, hey, start, run in the background, I'll tell you when to shut down. The simulator, you actually effectively halt the system in between the step or step 2 calls. Step just lets you effectively have the same behavior as the message bus. Step 2 allows you to move really fast forward in time. If you want to jump 5 seconds, you don't have to tick it a bunch. And it takes the same setup, except that you can actually seed the initial time in the system, and you can also seed the initial events in the system. So you don't have to like spam feed them in if you have a sort of playbook that you want to go through. And we also have, I also added hooks for on envelope publish event. So in the simulator, you can actually add hooks to record the events into some external system. So you can imagine you have a database like FoundationDB or Tiger Beetle that does deterministic simulation testing on tens of thousands of threads all the time, constantly. And what they're doing is they're running these random generations, Antithesis did a great talk on that. You shouldn't be using randomness, you should be using entropy. But basically, they're just serializing all of these events going through the system. And then when they hit that invariant, they can then take that serialized playback, run it through, figure out why that invariant was hit, and then it's like, okay, now we can actually solve these bugs really quickly, because that 1 in a billion event of happening, we can now replay that deterministically every time. And that's the whole point. Now you can imagine it's like 100 times more work to write everything as actors deterministic. It's like I can't just go talk to S3, I have to build an S3 actor and then send a message to it. And then but wait, do I make the S3 actor directly able to talk to HTTP, or does it like prepare the S3 message and then it sends it to an HTTP? It's like, you can imagine very quickly this explodes in complexity. And it only does that if you're, well, I say silly about it. Obviously, in a lot of databases, they go to the extreme and try to make the whole system deterministic. But you can be really precise with it. This meme was particularly fitting, but you don't need to make your entire database deterministic. You don't need to make your entire HTTP framework, do static site generations. These all don't need to be fully deterministic. You only need to put it where that critical logic is. So you can think in consensus algorithms. You want to make sure that your Paxos and that your Raft is like running correctly every single time, and if there are bugs, you can debug them easily. Merging and splitting algorithms. So if you're talking about key range spaces, or for ClickHouse, they use the columnar versions of that. When they decide how they want to merge and split stuff, you want to make sure you're doing that consistently. Your transaction system. So if you're thinking about guaranteeing some level of isolation, you want to make sure that you can drive that system consistently. And compute schedulers too. If you're launching things like pods and Kubernetes, you want to make sure that you can replay the decisions to put some logic of work on some unit of compute so that you can debug those systems. And if you want to abstract this, you can say you want to make deterministic the decision of what to do, not necessarily how to do it. So you can delegate off, hey, perform this request and give me the response. You can delegate that off to a non-deterministic system. But the way that you got to the decision to make that request, that's what you want to have as deterministic, so you can replay the events that led to that decision and debug any issues. And I think that's it. I don't have a Q&A slide. Does anyone have any questions? Yeah?
I noticed you use system time throughout the API.
Yeah.
How are you handling modifications to the system clock?
Yeah, I started with instant, but instant, I'm a lot more of a Rust noob than you are. After hearing your talk, I found that just manipulating and seeding an initial time into the system, it was a lot more difficult to do it with instant. So I went with system time, and if you look at the way that message bus works, it's just grabbing it from the clock. It's pulsing on doing some internal sleep, saying, hey, I've passed this much time. And then, if I remember correctly, I use system time because you're allowed to force increment it. And that's what the simulator uses with that dot step and dot step 2. You can force push it by some amount of time. After the questions, I will show you a quick run of the message bus and the simulator. Does anyone have any other questions? Yeah.
How this design differs from temporal one, for example, for Python?
Sorry, can you say that one?
Do you know temporal?
Yeah.
How the design of this system differs from the Python?
Yeah, okay, yeah.
Temporal.
So like temporal.io, so with durable execution, those events are much higher level, right? So they still do event replay, but in theory, there's nothing stopping your activities from changing their logic underneath. So you can think of it as a much lower level of abstraction of that same architecture of event replay. It's effectively the same thing as that, except now we're driving this at the logic level, where you're thinking of breaking down not just to sequential calls of functions being their own captures of events, but now you're thinking about like every line is now sort of that sequential event, durably captured event. Or the mental model I think about this is that you're passing messages around, is why I call it a message bus, rather than invoking something that you're expecting a response. You're decoupling that signal to response. I'm sure that wasn't the greatest explanation, but I have it pulled up here, and I have this really stupid test. The first one I'll show you, which is running through the message bus. I have this really simple ping pong subscriber where all it does is it will start emitting pings on. Oh, yes, absolutely. Sorry, I have a,
Make like 2 more.
Yep, let me get rid of that. Perfect, okay. Now the header's huge, but it's really simple. It just emits pings on some interval with some destination subscriber. And then this ping hold time, what it does is after that amount of time has passed, it will emit a pong back to the subscriber that sent it the ping. And you can see I have one set up as a priority of 0 and one as 1. Normally, ping pong 2 would emit first, but you'll see ping pong 1 will actually run first. And we can see, so this is the kind of point about clocks, right? So this is the message bus manually ticking for you. And you can see we apparently have about microsecond precision here, but you can see that every time we step, we're not at perfect intervals, right? Even though I've set it to, I think it was it 100 milliseconds or something? But you can see, we have these messages getting sent back and forth through the system. There's some associated time with them. Cool, that's great. It took 5 seconds because we ran the simulation for 5 seconds, right? Yeah, 5.01. Okay. Now, we can take that exact same simulation, or those exact same subscribers, and run it through the simulator. And what the simulator, we're going to seed it with just epoch time, and there's no initial events. And we're going to run it on simulated 100 millisecond intervals, so the same observed interval, but we're going to run it 50 times extremely quickly, right? And now what you're going to see is that this test runs immeasurably fast, 0 seconds. And now what we got is we got the same sequence of events, so you can see, sending ping from 1 and 2, and then you can see that at some point in time, we went from not responding to them at all to at exactly 1 second, the exact amount of time we said we're going to hold for, we now start responding with pongs. And you can also see now that we are stepping exactly on 100 millisecond time, which this is the level of control that, one, we say we can't get this in the real world, so we have to simulate it, which means we can now drive that deterministic behavior because we control the clocks perfectly. So we've effectively simulated the clock. And this is how you can run these, effectively fuzzing events into your system super fast. And, I think on like Tigerbeetle's website, they say they run like a year every like 7 seconds or something. A year's worth of simulation time in 7 seconds, or I might even be conservative with those numbers, I don't remember, but you can run it incredibly quickly because we can just simulate the passing of time at basically as fast as the CPU will process it. We don't have to wait for time to actually pass. Yeah, does anyone else have any other questions? Yeah?
I don't know if I'm right on this one, but basically like if you are stepping through time and you have an event that actually like takes longer than 1 cycle, would not that mess up with the system?
No, so if you have, so again, this is why we observe the passing of time instead of like actually physically waiting. So if you have, say, an event that's going to sleep for 300 milliseconds, it's only going to sleep for 3 steps of that 300 milliseconds. So it's still going to happen instantaneously because, again, instead of physically waiting for a time.sleep or whatever the Rust equivalent is, we're actually just saying, all right, there is some time I responded to. Either tick was called or receive was called. I learned about some time. I did something, and I say, OK, I want to wait 300 milliseconds before doing some other thing. So instead of actually sleeping, I'm now internally storing in my memory, OK, when the time hits this or later, I'm going to now do this thing. So you can imagine storing some private variable saying target time n plus 300. OK, now I got a tick. It wasn't there. Tick wasn't there. Tick. Oh, yep, we hit that time. Now I'm going to respond to this event, do this thing, generate this envelope, and return that back into the message bus or the simulator. Yeah. Yeah?
I'm not sure if this is the same question or not, but sleep is obviously one way that we can pass a time threshold.
Yeah.
But imagine if your response to the tick function ran a loop 300 billion times, and it didn't sleep for 300 milliseconds, but it did, say, miss the next tick. How does the system handle what would be like blocking the main loop?
Yeah, exactly. So the message bus is single-threaded. So you want to spend as little time as possible blocking that receive or that tick function call. That's why if you want to do something compute heavy or time heavy, you want to kick it off to your own background thread. IOU ring, again, best example of this, where they say, like, I'm going to relieve the caller of me doing my work. That's like the forced synchronous model, if you want to call it that. Or sorry, forced asynchronous model, if you want to call it that, where it says, you spin and kick rocks until I'm done, right? So that's where you just want to be really careful about how long you're locking up that thread, because if you are locking up the thread, not just from one actor, but collectively longer than your tick, you're going to start running into the software equivalent of if you ever play Minecraft and you load too many chunks at once and like everything in the world is frozen and then it all happens really fast because the amount of time it took to process all that stuff was longer than the tick of Minecraft. It's basically that, but in whatever software you've written's world. So you do have to be very mindful about how long your code is taking to run. Yeah. Cool. Awesome. Thank you so much.
All right, yeah. So I titled the talk, Rust is cool. What if we made it boring? Because I think that REST APIs are pretty boring. It's like not what we think of when we want to use Rust. Usually you use Rust something low level, like a database or a something that replays requests, like fancy things that are cool. But I think my career so far has very much been one of a crud monkey, to be direct about it. And I haven't really worked on low-level systems. So I think the interesting thing here is that Rust is actually pretty good at this boring use case, even though you wouldn't think it would be. I put my @ here if you want to follow. The presentation is live at rust.skeptrune.com if you want to view it in your own browser or after the talk. So API-first companies are huge. I think when I was starting my company, which was called Treve, I wanted to make it API-first because I was like, there are really big API-first companies, and if you succeed at it, you don't have to build a lot of front end. And I was definitely trying to avoid having to build things like a pretty dashboard and user experience. So I put some of them on this list. My company was a search API company, very analogous to Algolia. That was kind of like my core inspiration. But yeah, I think this is a kind of a good reason to care about the problem. It's like building HTTP APIs with high quality documentation is valuable and important, like something that is worth it to get right. And this is kind of like, I'm sure everyone knows what REST API is, probably. I think a funny thing that I ask in interviews sometimes when I'm interviewing people is like explain the difference between a resource and an endpoint. It's like weird niche knowledge that kind of reveals to what extent you have been a crud monkey so far in your career. Resources are going to be nouns. So like you could have a user or a car or a home, and then your endpoints are the nouns plus the verbs. So get, post, delete. Post means create in most APIs. People don't really adhere to these anymore. Often you can just use post for everything. But this is kind of like the broad stroke point. And when people are using your API, they have to figure out which resource and which endpoint to use in what order. So it becomes really, really important that you display this information to them in a way they can understand. This was the OpenAPI reference for Treve. It's a Mintlify site. I work at Mintlify now, so I thought this would be interesting. And it looks kind of nice. Like you can see on the left side, there's a chunk resourced and several different endpoints. And then you kind of have like a big blurb of text in the center here, along with a heading, and then an example of how to do that request in curl that you can copy right into your terminal. It looks nice and it's kind of like easy to consume. The problem that I initially had founding my company is that I didn't know how to get these pages to render. Like it's not very intuitive if you've never done it before. And I didn't know like what to feed into systems like Mintlify for this to happen. So I started manually creating these pages. Like I was writing all this text by hand for each endpoint, which is infeasible as your product grows. Something like Stripe, or in my company, you have hundreds of different endpoints. So you cannot continue to maintain this manually. You add one field to the request object, and then you're going into 14 different routes to add it. And the usability of your product quickly becomes poor. Under the hood of a page like that is raw JSON. And the raw JSON looks like this. It's very ugly. You have raw text in each API path, an object that exists in the API. And this is the thing that I was writing manually in the beginning. I was like opening this JSON file and manually tweaking stuff. It's gotten a lot easier with AI, but I think it's still very, very hard to do this accurately. And a lot of existing languages outside of Rails still do this poorly. Dan was talking about Go earlier. Go is still bad at this. There's not a good library in Go for generating these open API specs. There's definitely not a good library for .NET, despite .NET's ubiquitousness in API-driven development. JavaScript Express is like horrible. Alicia is a little bit cool. You can kind of get it out of the box, but traditionally it's very hard to do in JavaScript. And Rust is actually like weirdly great at it. And the strong type safety that exists in Rust allows you to get this accurate and correct to a much larger extent than you can in other frameworks and their languages. So I think this is kind of like the core, like the ability to generate this JSON file is the core reason why Rust is good at REST APIs. And the library that you do that with in Rust is called Utoipa. It's a play on the word utopia, and I think it is kind of a utopia. It's like a really, really amazing library. And this code sample here is what would go at the very top of your lib.rs file for defining, like, at a high level what your API is going to do. So here I'm putting the dev URL, localhost 8090, the prod URL for the API, api.tree.ai, and then information about it, what the license is, the title, the version, so on and so forth. You can also like register each of your schemas that you're using the API. So like here, you're kind of seeing me register the create dataset request payload. And you can register all of your responses there as well, along with different paths that exist in your API. It's really, really smooth and easy. And even as you add hundreds of routes, this can get a little bit long, but it's very composable and easy to read, to add, and edit. And the errors that come out of Utoipa when the compiler is unhappy, make sure that you're getting it correct. Like your code just won't compile if it's wrong. You don't have this benefit in other languages, other frameworks. Other cool thing about Utoipa is that you can actually serve like the old school version of doc sites, so Swagger or Redoc. They look a little bit uglier than Mintlify, but they work. And you can serve them right from your server. So whenever you redeploy, your docs automatically redeploy right alongside. You don't have to make sure you kick off a job to Mintlify or some other service. And again, like for your power users, people that really care, for the old heads, they love this. It's a sign of reliability and like trust. And again, it's really hard to do this outside of Rails. Like Rails, Rust, you can do it. Most other things, achieving this is hours of work and custom stuff. I think this is a really good example of like a single route in Utoipa. I think whenever you look at this, you can see the title at the very top, a brief description of what it does, and then information about the API route. So it's a post request, this is the path, it's /API, here's the request body, here are your status codes and responses, here are the params, use an API key. The API key has to be an owner type. It's great, it's easy, and it's in code. Like it's actually in your .rs files. So you're not having to edit that JSON manually. There's a macro that generates the JSON for you based on your actual code. And kind of like the key to this to me is create dataset request payload. Like this is your struct that defines your API request data, and it's very important this is accurate in the final specification. And because it is here as a struct in and of itself, you don't have to update it manually. The minute you update it inside of your actual request handler or route handler, it'll update in your spec. That's kind of like what I think is the core of what makes Rust great. This is kind of, I guess, the sugar on top, or the sprinkles, if you will, why I also like it. The pattern for building REST APIs, kind of regardless of which HTTP framework you use, between Actix or Axum or whichever, is like the canonical way to do it, if you look at a lot of open source repositories, is the handler operator pattern. And it's very, I think in Rust, it actually happens because people do a thing where they start building a product as a REST API, then it becomes gRPC. So like at some point, they have to migrate to Tonic. And during that like migration from REST to gRPC, this pattern like holds up because you take your handler layer and you leave that alone, like that continues to serve a REST API. And then you add a gRPC layer kind of like to the right here, and that gRPC layer points to your operators. So you reuse most of your business logic, you just kind of like add a new interface. And again, like whenever you look at open source .NET libraries or JavaScript libraries, like there's an incredible amount of diversity in the way they structure their APIs. And I don't like that. Like you want there to be kind of one way of doing things, if you will. And in the Rust world, like you will pretty quickly get open source people yelling at you if you don't do it this particular way. And I think that's a big benefit. Like, it also is not moving very quickly. I think since I started doing this 4 years ago, it's the same shit. .NET's like always changing, very dynamic and annoying. So I think this is like underrated, you know, kind of hidden, but architecture is important. Also like OLTP, DB, ORMs. We talked about SQLx earlier. I use Diesel in my product. I think regardless, the point is that they're good in Rust. Whether you use Diesel or SQLx, whatever, I think you're gonna have a good time. I put an example of a fucked up Diesel query here. Like it is weird and matching the errors and stuff is odd. But you can get by and like it's nice, I think no matter what you do, and like support for it is good, whereas like support for ORMs and Go, I don't know, not as robust in terms of the migration files. Yeah, okay. And then final thing I think here is it's very hard to mess up when you use Rust for REST APIs. Put Clippy on extra strict, don't unwrap, make sure Utopia is using all of your types, and you can go really, really fast. You can vibe code a lot in that backend because you know it's safe as you go. And I think that's just like huge, huge benefit in the modern day when you're trying to not waste your time being a crud monkey. Like you want to work on more enduring, harder problems. So Rust allows you to do that very safely. Pro tips. So one, like market the hell out of an API product. I definitely didn't do enough marketing with mine. It's more of a business tip. But on the actual like code tip, the Rust HTTP servers, so Actix and Axum, do not come with a default timeout, which you would think that they do, but they don't. So like requests can just take 2 minutes and they don't cancel them. Yeah. I just assumed this was like a thing, and then I took down prod like a few times for customers because we didn't have timeouts. So like inside of the middleware, no matter what you use, when you start a new Rust project as an HTTP server, add a timeout. Pro tip, like first thing that you should do, make sure that you're timing out your requests that take longer than 10 seconds. I think funny story, when Denzel and I were starting, we were like too broke to afford analytics services. Like we did not have enough money for Datadog or Sentry. It was like too expensive. We were to search APIs. You can imagine very quickly we had a lot of volume on the API. So what we did is we got like a cheap ass Twilio token, and inside of our server we had like raw Twilio code to call our cell phones if requests timed out. So I remember like very early on, we had gotten like our first 10 customers or like 20 customers in the YC batch, and we were meeting with VCs in person during the batch. And I would go to these like, VCs' offices, my phone would just not stop fucking ringing because the thing would go down and like have to restart probably once every 15, 20 minutes. And I remember like it was pretty good for fundraising because I would tell the VCs to be like, we have so much traffic, servers won't stay up, I keep getting called. Yeah, definitely like, it took Denzel and I about 2 weeks to like understand that they're like how to do this. It's like it's very unintuitive in Actix and Axum. And there's like, and none of the templates have it. So like the AI doesn't know how the fuck to do it. There's no documentation. It's not good. Yeah, that's like the whole presentation. Promotion for one of my open source libraries called Sherp. I made this using a tool that converts Markdown to presentations. It's cool. It's called Sherp. This is the URL to Sherp. If you're interested in vibe coding presentations without having to use Gemini to make images, it's a fantastic tool. Cool, yeah, that's the presentation. Anyone have any questions before we close it up? In the back.
Yeah, have you seen loco.rs?
Yeah.
Yeah, loco.rs absolutely slaps, and I just am trying to convince all of my friends that I can write like personal projects faster with like Axum and like nice RESTful APIs, and they all just laugh at me and think, so I guess this isn't really a question, but I'm just wondering if you have tips for convincing people that like RESTful APIs. I mean, you've done it right now, but yeah, it's not a question.
I think there's actually some real stuff to that. The big problem with Loco is that it doesn't have support for rake or any of the other like niceties that Rails has. So I think it's like hard to sell people on Loco still because there's not like that story for async queues and stuff like that. There's a random Hacker News thread that I left a comment on, like specifically talking about Loco and like kind of my not belief in it. Just because I think that like it's way easier to compose your own shit on Actix or Axum. The critical thing I would tell you is you need to like show your friends this library. I feel like people that have like serious concerns about using Rust for REST APIs, the most valid reason is there's not a story for background queue systems. And Broccoli does like a great job. We wrote it at Shreve because there's not a great one that exists for it. So I was trying to recommend like showing them this over Loco. Other things like, if I recall correctly, Loco uses mini Jinja, and no one wants to fucking use ERB again. Like whatever the modern equivalent of ERB is, still not good. So yeah, maybe don't convince them of Loco. Just convince them of like break it down for like more of a bare bones perspective. It's easier to explain to people, in my opinion. Yeah, arguing about this on Hacker News, I guess.
Also, this will be posted to YouTube.
Yeah. Anyone else? Dan, what's up?
So should we just use gRPC instead?
You know, like, it's actually an interesting question because
So we want our PCs, right? We don't want a bunch of verbs.
I think like the interesting thing about HTTP APIs versus gRPC is that vibe coders have a much easier time consuming HTTP APIs than they do gRPC SDKs. So like a great example of this is actually Stripe. The library for Stripe in Rust, it's called async Stripe. Anyone ever use it? Yeah, you guys haven't built B2B SaaS in Rust. Async Stripe is a monstrosity. It's like absolutely horrible. And the fact that Stripe is not gRPC and is rather an HTTP API means you can kind of like short circuit having to deal with the fucked up SDK by just making HTTP requests. And for that reason, I think like if you're building a B2B SaaS company, it is.
Wanting your revenue.
Hey, let's go, close one. More than
It is. But I think I just say like there's actually an interesting point in that it's way easier when you're starting a new business to do HTTP REST APIs over gRPC because you don't have to sell people on an SDK. Yeah.
I have a second question.
Sure.
You said after you were in YC, you couldn't afford analytics services?
No, before.
Okay.
Denzel and I were like doing this for about a year before we got into NYC. Ironically, doing e-discovery.
It's expensive, but
Yeah, no, we could after. We were just stubborn. Yeah, okay, that's all I have. Anyone else? Final questions? Cool.